Well, how's everybody doing? Like we have four of us.
I'm good.
I guess we have, yeah, four of you and one of me. I guess that makes five, doesn't it?
I'm doing good.
That's good. Yeah, it's nice having better weather that we can be outside. We haven't spent a lot of time outside.
As if I'm actually going to go outside.
Well, go ahead.
I was just saying we're good over here too. So
Good. Everybody's well? I haven't heard of anybody in the school getting sick other than the one parent, so it's been good.
Yep.
So are we ready for section review 17.2? This one doesn't have much math or anything like that. It's more concepts. I guess there is a little bit of math on number 5, but not a lot. So why don't we, I'm pretty sure I have it recording already.
Yep.
Okay, want to make sure of that. So let's start with number 1. It says, what is studied in the branch of chemistry that is known as chemical kinetics? Or would someone give us an answer that they have for that one already?
Reaction rates and reaction mechanisms.
Okay, those are the two things that are studied in chemical kinetics, right? The first ones are kind of the easier questions, and then they have some that are a little harder. Okay, number 2, list 5 important factors that influence the rate of a chemical reaction. Since we have 5 people here, why don't each of you give me one? Starting with William.
Nature of reactants.
Okay, nature of the reactants. Let's see, next on my list I have is Hallie.
I was going to say temperature, but I don't know if that's right.
Temperature, okay. Okay, temperature is another one, that's good. Let's see, Catherine.
surface area.
Surface area would be a third one. Daniel.
Has concentration been said yet?
Nope, hasn't been said yet.
Okay, concentration.
Okay, so far we have nature of the reactant, surface area, concentration, temperature, and Reese. What is our 5th one? Or Josh, or Malia, either one of you could give me, what's the 5th one that we haven't listed for factors? We're doing number 2 on the section review. Pretty quiet. Oh,
Reese said it in the chat thing.
Reese is texting, so he's saying presence of a catalyst. There's our 5th one. There you go. That works for me. If we can do that way. I don't have to worry about, did I hear you correctly? I can read. Okay, so that takes care of number 2. Number 3, what is a catalyst? Explain the effect of a catalyst on the chemical reaction. And then how does the catalyst influence the activation energy required by a particular reaction? So let's first define it. So would somebody define what is a catalyst?
A substance that changes the rate of a chemical reaction.
Okay, and why don't we add one more thing? What happens to it, or what's true of it when you get to the end of the reaction? Let's say it that way. When you get to the end of the reaction, what's true of the catalyst?
Not permanently consumed.
Okay, not permanently consumed. Why don't you add that on the end of it to make it complete? Okay, so it's a substance that increases the rate of a chemical reaction without itself being permanently consumed. It's very actively involved in forming that activated complex, but by the time it gets to the end of the reaction, it's totally extracted itself out of all the products, and it's there again to be used all over. Okay, so that takes care of the first question. Now, what is the effect of a catalyst on the rate of a chemical reaction? Well, I think you kind of said that, so we can probably go on. Because I think, William, you said it increased the rate, right?
Yeah.
Okay, so we covered that one. We did both of those all in our first answer. Okay, so then how does a catalyst influence the activation energy required by a particular reaction? Anybody have some answers?
It provides the alternate pathways.
Okay, provides an alternate pathway, and they're asking a little bit about energy. So what is true when it has this alternate pathway? What's true of the energy?
There's more of it.
And I guess I wouldn't say it that way. What's true of the activation energy?
It's lowered.
Okay, it's lowered. Reese says it lowers the amount of activation energy required. Very good, Reese. Okay, so it provides an alternate pathway, energy pathway, and it lowers the activation energy. Anybody need a little more time on that one? Okay, if not, then let's go on to number 4. What is meant by the rate law for a chemical reaction? You can either speak it or you can type it. You can type faster. That's great.
An equation that relates reaction rate and concentrations of reactants is called the rate law.
There you go. Okay, so it's an equation that's relating two things: the rate law, the reaction rate, sorry, and the concentration of the reactants. So if you've watched the video, lecture video, you saw always they had R, that's the reaction rate. And on the other side, we had the things in brackets. Those were our concentrations. Okay, next it says, explain the conditions under which a rate law can be written from a chemical equation. This one we'll have to see if you got that from what I lectured or not, or how well I did, I guess.
I wrote, if it is a single step reaction, you can use the chemical equation, but if it requires multiple steps, you cannot.
Okay, you answered the rest of the whole question. Good. Okay, so
Oops.
if it's a single step, then you can take it straight from the chemical equation. The coefficients become exponents and stuff like that. But if it's not a single step, it's multi-step, then you have to do it experimentally. And I think we had like sample problems B and, was it B and C? Or is it A and B? That had tables of data that you had to use to figure out what the exponents were. So, but that was because they were multi-step. So single step, you can take it straight from the chemical equation. Multi-step, you have to do an experiment to gather the data. Okay, now on number 5, this is the one where we get to apply a little bit of math. And I know that some of you, that's not your favorite thing, but I'm going to try to hopefully make this as a little easier for you to do, because these type of questions are great test questions, and I'd like you to be able to do those. So they gave us this equation right here, R equals K x to the third times y. Now, what I like to do in explaining this is let's take out the brackets and just have K x cubed y, okay? Now, let's look at problem A. And they want to know, what is the effect on the rate of the concentration of y, or if the concentration of y is reduced by a third, and then x remains constant. So back to that original equation, we'll write down what they're actually saying. It says y is going to be 1/3. So we still have x to the third power, but in here in place of y, we have 1/3 y. Now, if we take out those brackets, we would have R equals K x to the third y, and then I can move the 1/3 all the way up front. So how does this answer compare with this answer? In other words, if I'm comparing these two, what's different? I have the rate is equal to a third. So if I reduce y by a third, I reduce my rate by 1/3. So I'm looking for, so when you're doing these kind of problems, when you get to the end, try to move all the number parts up front, and then you have your variables after it. So I move this 1/3 all the way to the front here, so I have 1/3. So then all I have to do to figure out what happened to the rate is just look at the number. The rate is equal to 1/3. I hope that's helpful. Okay, that was A. So now let's do B. So if you use that same method for B, it says that if the concentration of X is doubled, but Y remains constant. So for B, we're going to have X is doubled. So instead of X on the inside, I'm going to have 2X cubed. And it says nothing's changing in Y. Okay, so if I do this, what number will I have up front? I want to get it so I have R equals, and then I want a number right here in front of a K X cubed Y. What's that number right there?
Is it 2?
Well, what do I, when I look at this concentration here, and that's cubed, I get an X cubed, but I get a number. What's 2 cubed?
4.
8.
8. Okay, so this number
2
right here
cubed.
becomes an 8 because the 2 is cubed. So that's 8. So when I'd have like 8 X cubed Y, and then I like to move this up front so I can answer the question that it's So that means that the rate will now be how many times more?
8.
8 times more. Very good. Okay, now see, what is the effect on the rate if a catalyst is added to that? So here's this up here. What would happen if we added a catalyst?
Increases the rate of the reaction.
Okay, yeah, we know that a catalyst increases the rate of the reaction. Now, here's a little extra that's not, they're not asking to do that, but what up here in this original equation, what up here gets changed when I add a catalyst? What in this original equation up here gets changed when I add a catalyst?
Is it the R?
Yes, it will change the R. Very good. And if these others aren't changed, then what else has to also change if R gets changed? So adding a catalyst changes R.
Isn't it like that you have to, what you do on one side, you have to do the other?
Yeah, you have to do something over here. So these are concentrations right here, so they're not changing. The only other thing that could change is what? It changes the K. In other words, remember every chemical reaction under certain conditions has a certain K. Well, adding a catalyst makes the K become a different number.
Isn't K standing for constant?
Yeah, K stands for constant in it. So when I put a catalyst in there, I have a new constant. Good question.
I just forgot. I just want to make sure.
So remember that I think one of the things I said in my lectures about that K fits a very specific set of conditions and reactants, and you change the conditions or the reactants, and changing the conditions would be like adding a catalyst, then you're going to have a different K. So yeah, I did change the K. But they're not asking for that in C, but that is a bonus. Okay, so let's look at 6. Is it correct to say that a catalyst affects the speed of the reaction, but does not take part in the reaction? From what I said a little bit ago, what would be the answer?
No.
No.
Okay, the answer would be no. And how did I say that? Or in your own
Because
way? Say what?
the catalyst affects changes the constant in the reaction.
Okay, and the catalyst does take part in the reaction. If it were actually used up, then we could only use it once. But we've said that it became part of the activated complex along the way, and then extracts itself out at the very end. So there's no change in the amount of catalyst I have. So it does affect the speed, but it very actively becomes part of it, because back up there in, I think it was question 3, we said that it provides an alternate energy pathway. And then it lowers the activation energy. So all of that is included in this idea here that yes, it does affect the speed. Yes, it takes part, it very intimately takes part so that we can have an alternate energy pathway. But if you started out with 10 grams of catalyst at the beginning, at the end, you'd have 10 grams of catalyst. You could use it all over again. Okay, so then let's go on to number 7. Okay, number 7, it says to the right of the is an energy diagram for a particular process. One curve represents the energy profile for an uncatalyzed reaction. In other words, a reaction without a catalyst. The other curve represents the energy profile for a catalyzed reaction, one that has a catalyst in it. Okay, A, which curve has the greater activation energy?
A.
Okay, remember activation energy, if I'm gonna, what do we start with right here? What's in this corner where all these lines are meeting? What do we have right in this place right here? I'm beginning with the, starts with an R, give you,
Reactants.
now let's start with the reactants. And if I were to draw a dotted line along here and draw an arrow from that dotted line all the way up to here, I have the activation energy, EA, and this is for an uncatalyzed one. This would be the EA for a catalyzed one. We're going to call that one prime because, or double prime or whatever you want to call it, but it's for a different one. Okay. So A would be the right answer for the first one. Which curve has the greater energy change? Now, remember where delta E went from? Where did it go from? Where to where?
It goes from the activate that line, the
Yeah.
dotted line you have, and it goes to the highest activation point.
That's activation energy. I think here they want delta E though.
B. Or wait, never mind. Or B.
Down here, remember where's the products?
A. A.
It's going to be the well, okay, we need to go back. Delta E is from here down to here. That's our delta E. How much energy did my product, my reactants gain or lose to become products? This one lost that much energy. So the question is now, if this is the delta E that they're asking about, which curve which has the greater energy now? Now that you know that is true, which has a greater energy? Afraid to answer. Don't they all start right here? And they all end up right here. Yes, this
So they're equal.
activation energies, but this part right here is the same for both of them, isn't it? So what would be our correct answer for B?
C.
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 It's going to be C. They both have equal energy. This one goes from here to here, whether it goes this way or this way, they both go from this level to this level, right? So this is delta. I hope we're not getting this thing confused with our activation energy. The amount of energy involved over the whole path is probably greater for number one. That's true. But they're asking just for how much. Delta E is just what's the difference in energy in products and reactants. Reactants and products. I pointed it wrong. That's what they're asking about for B. Okay, and then C, question C, which curve represents the catalyzed process? This one's easier.
B.
It's going to be B, curve 2. That is the one with the catalyst. Remember, it lowers the activation energy. Then D, it says, explain your answer to part C.
Isn't that because it lowers the activation energy, like you just said?
Right, because it lowers the activation energy, right. You can add other things to it, but that's that's the heart of it. Okay, I think now we're ready for 8. Okay, it says, explain the following using the collision theory. Okay, so let's review a little bit about collision theory. That was the one that in order for molecules or ions to react, they have to collide. And what were the things that we learned that had to be true of those collisions?
They had to be at a high enough speed.
Okay, high enough speed, high enough energy, and
They had to be
Correct
correctly oriented.
orientation.
okay, correct angle, proper orientation, any wording like that. Okay, so that's what we mean by the collision theory. Okay, so now let's go back and look at A. It says gaseous reactants react faster under high pressure than under low pressure. So now we have to add one more thing to it. What does, what's true of a gas under pressure, or what causes pressure? Maybe you should say that.
A closer enclosed area.
Okay, so you're going to have pressure is caused by being in an enclosed area or a smaller area. And let's hang on to that thought. And then what actually causes pressure, like gas pressure? Pressure is
An enclosed area.
okay, we have that. Just hang on to that. But what do the
Okay.
molecules have to do to cause pressure?
Doesn't it have to do with the collision rate?
Okay, so pressure is caused by collisions
Thank you, Reese.
where they're bumping into each other. And then with the idea of in a closed area or a smaller area, if I put them in a smaller area, what happens? Or do the
There's more collisions.
okay, smaller area equals more collisions. Okay, now with the collision theory, okay, we went over that. So why is it that gaseous reactants react faster under high pressure than low pressure? So taking the theory and then apply it to this.
Because there's more collisions, so it's more likely to meet the standard.
Okay, more collisions, it's going to be more likely to meet the standards of fast and, colliding with enough energy and proper orientation. Missed a word in my sentence there, or in my phrase. Okay, let's look at B. Ionic compounds react faster in solutions than as solids. Now, this is a question that's going to take you back some chapters to see if what we remember about ions in solution.
I try not to think about that.
how much movement do ions have in a solid?
Not a lot.
Not a lot. They're pretty much in fixed positions. What's true of the movement of ions when you put them in solution?
Speeds it up.
Yeah, they're free to move around, so they're going to speed up. So if they can't move like they are in a solid, collisions is going to be pretty difficult. But if they dissolve in a solvent, they're free to move around. Movement allows collisions. Okay, then on to C. A class of heterogeneous catalysts called surface catalysts work best as a fine powder.
That has to do with the surface area, right?
What did you say, surface area?
Yeah, the amount of surface area of this looks
Right.
exposed.
Okay, so if they have more surface area, there's going to be more places for them to collide and get the help they need.
So that has to do with the proper orientation, correct?
Yeah, all those things that we said before would have to be true. It's just that when they collide with the catalyst present, it's going to make it go faster, require less activation energy. So there's more surface available for more collisions to allow a reaction. And yes, it has less energy. I think we had a question earlier on one of the assignments that was kind of related to that. I'm not sure everybody got it maybe as well as we, when the activation energy is lowered, what happens to the rate of the reaction? We said it moved faster if you lower the reaction rate, the activation energy. And why is that? Well, at a given amount of energy, you're going to have more atoms that have that much activation energy. A larger percentage will have that much activation energy, and there are going to be more of them that get to react. I think I used the analogies of like you've had $100 and if you went to a concert that costs $10, you could get 10 people listening to the concert, but if it costs $50, there's only 2. So with $100, I could have a lot more of them be able to attend the concert. In other words, participate in the reaction, I guess. By the way, what are heterogeneous catalysts? What does that mean?
It means not homogeneous.
Yeah, very good.
Yeah.
Homogeneous. Homogeneous. So
When it's,
go ahead.
oh, so I was going to say when its phase is different from from that of the reactants.
Okay, so if your reactants are in one phase, but the catalyst is in a different phase. A really good example of this is your car. I think almost every vehicle anymore, except for maybe semis, have a catalytic converter underneath the car. And the exhaust gases, in other words, they're in that phase, gaseous phase, go through the catalytic converter. And in the catalytic converter, they have catalysts coating the surface of pieces of metal. And they're solids. So they are a heterogeneous catalyst to the gaseous reactants coming out of the car engine. You'd think, why are there reactants? You think it'd be products. Yeah, it's mostly products, but there's some molecules that still haven't reacted yet, and we're providing a lower energy so more of these will finish reacting. Okay, I guess we're ready for the last one?
Woo.
So, number 9. Okay, using the idea of reaction kinetics, explain the purpose of food refrigeration. Now, what's the obvious thing why we put things in the refrigerator?
So they won't go bad.
What? So they won't go bad, right? So when food goes bad, that process of going bad is a chemical reaction, isn't it?
Yes.
So putting food in a refrigerator does what to the chemical reaction?
Slows
It
it down.
slows it.
Yeah, it slows it down. Remember, you said one of your, I think this was question, was it 2? What's one of the factors that influences the rate of a chemical reaction? And that was temperature. And so you lower the temperature, you lower the reaction rate. Now, probably the only thing that would maybe stop the chemical reaction is to make it, maybe freeze it. You know, where the molecules move still even slower, but food in a refrigerator won't last forever. You just slow down the spoilage rate of reaction. So, any questions you have?
How are you doing, Mr. Hubert?
How am I doing? I guess pretty good. We're getting down to the end. When we finish this chapter, we'll start into the next chapter, but we won't even be able to finish it because school's going to be out before that. So we are getting to the end.
So, what am I going to do? Because I'm a senior and stuff and can get out earlier.
Yeah, so this is a senior answer for Hallie, not anybody else in here. Yeah, you'll be taking semester tests, I think. So you're out on the, what day is that?
8th. We're out on the 8th.
Yeah, on the 8th. So, and Mr. Hood told me what day, or told us as teachers, what day science finals will be for seniors. Or wasn't it for seniors? Maybe that was for everybody. So anyway, yeah, you'll have if you have an A, you don't have a final, but if you don't have an A, you'll have a final. Now, let me tell you this one thing, and for finals, and this will be for everybody, not just Hallie. Yes, it'll be over all the chapters we've covered this semester, but they're only going to be multiple choice questions. There won't be any where you have, like we had on the last one, where you had to work out something and you couldn't pick an answer. You don't have to show your work on the final, but then you don't have a chance either at getting partial credit.
So how are we supposed to study for the final if you have our test?
What I'm going to do actually the same thing I do ordinarily, but yeah, you have the tests. I'm going to put all the old tests online, kind of like your quizzes are online. I'm not sure exactly how I'll go about doing that yet. because teams create certain limitations. Well, what we might do, would this mess with anybody if I go back to the way I've always been doing it and I put it in facts under resources?
No.
Okay, if that wouldn't, I'll just do that like we've always been and not do the review through teams. So I'll put all the tests that we've had this semester. I can actually put them all up through chapter 15. I can put those up already if anybody wants to start reviewing, but I know that there's not many that have thought about reviewing yet. But that's, we'll just make the test easier for you and also easier for me to grade. You're just going to do the multiple choice ones. And if there's any matching, I don't know if there's any matching, but mostly just multiple choice. So any of the questions that aren't multiple choice, you don't have to study those. Does that answer your question, Alex? Okay,
Mr.
good.
Hubert,
Yeah.
what are we going to do about a review for this test? Is the test for chapter 17 close, or are we going to have like a couple days where we do something else, or should we expect a review like tomorrow?
Oh, you're you're expecting to have to take the test this week. Now your test's not until I think it's next Tuesday. What we're doing is tomorrow I have one more section in the chapter that kind of ties up, covers a few smaller details that we haven't covered yet. And then the only thing that's due tomorrow is this review packet that we talked about. And then on Wednesday, Thursday, and Friday, we're going to be doing a lab. On Wednesday, it's a pre-lab, and that everybody does, and you just turn it in like an assignment would be. And then on Thursday and Friday, the lab is going to be, it's over reaction rates. And we're going to, like we did learned in a little earlier in this chapter about figuring out what the exponents are for a chemical reaction. You're going to do that same thing. You're going to gather your own data. But I'm going to do the experiment and videotape myself experimenting. And then you just watch it and time the reactions. Your only thing that you have to do is run a stopwatch, either on your, if you actually have a stopwatch, you can use that. But most of you probably have a cell phone that has a stopwatch or a timer on it. And you just time the reaction. You can just watch when I start it, and then you're going to be looking for something to happen. And then when it happens, you record the amount of time. So that's all that you really have to do. Is other than that, you're just watching me carry out the chemical reaction, but you're gathering your own data in the experiment, and then you'll figure out what are the exponents for the concentrations of the reactants. It'll be just kind of like doing your own, gathering your own data and doing kind of like we did, what was it? Not yesterday's assignment. I think it was last Friday's assignment, maybe is when we went over that kind of stuff. But anyway, back to your question, Catherine, is so we won't review for the test, I think, until next Monday. Now, have let's see, I think tomorrow I'm supposed to, I think on my lesson plan is to give you the chapter review questions. So then you'll have from tomorrow till they're due next Monday if you want to get your 3-point bonus.
Okay, thank you.
You're welcome. Anyone else? Well, if not, this is going to be our shortest help session so far. So just hang in there, guys. It's not, not that long anymore. Let's see, Hallie, you have the 8 days in May, and then you have, what, 3 more days this week in April? You're down to what, 11 days?
I don't want to talk about it, man.
You don't want to talk about it. Okay, we won't. And the rest of you have 1 week more. Well, have a good evening or rest of your day.
Thanks, you too.
You too.
Bye-bye.
Bye.